Hello, everyone. I'm Smadar, the CEO of Vanti Analytics, a self-service platform for manufacturing experts to achieve operational excellence through leveraging the data you already collect. Today, I'll go through the different steps and lay out a fairly simple framework to enable successful AI applications in manufacturing. So what we'll cover is the motivation first to go after machine learning and AI in manufacturing, some of the logic behind it, which will help to understand the reasoning behind the data we're aiming for. And we'll talk about the different aspects of the data, quality, traceability, and amounts. And then we'll touch a bit on the ongoing results and deployment before we summarize and conclude. So the motivation to seek for value from data stems from the modern challenges in manufacturing. Long root cause cycles, line variations, they all waste time and materials, and product launches or updates are more frequent than ever. Brand reputation is crucial in our competitive environment, and add to that the recent challenges around supply chains and material shortages. We understand that we have to minimize our defect rate and to do it as early as possible in the process. So this is how the vision we all look and seek for, right? Predictable processes, actionable insights, streamlined into the production, optimizing every step. So starting from which materials to use, what should be the parameters for each assembly process, all the way to the actual behavior of units in the field. So before jumping to what should be in the data and how it should look like, it's beneficial to understand better what are we trying to accomplish. So we want to understand the mechanistic behind our manufacturing process. And there should be one, because eventually we're trying to describe a real-world physical process. So if we get to that understanding through the data, then detecting anomalies would be an easier task. For algorithms, of course, not necessarily for a human being, because it's usually too many parameters and dependencies to consider. So taking an engineering approach solves also the potential explainability of these anomalies, which we'll touch on a bit later. So now that we understand what we're trying to achieve, it's easier to understand what data should we go after. So from an engineering perspective, we're looking for everything that drives the behavior of our products and processes, namely the materials and components, which are usually in the incoming or outgoing quality checks and inspection points. Machine setups and configurations defined by the machine logs can be found in the machine logs or collected by the sensors. Measurements and test results tested on the ATEs, optical inspection points such as AOI, X-ray, and so on. And of course, any other testing point that is documented. So let's look at a simple example, data from an active alignment process. So high quality data here documents almost everything that we can imagine that would have an impact on the process. So the time, which machine was it, the adhesive type used in the process, its physical properties, the process parameters, and so on. So you may have implemented an MES software or built out a customized database, or you have both. But in any case, the ability to track a process or a product through the different stages is very crucial for developing meaningful and useful algorithms. So if we want to be able to describe a product or a process behavior, we need to associate every point of data with its relevant unit or process. So how would that look like? Let's look at an example from assembly of modules and tests. So here we see results for every serial number. We see the measurements in the machine process configurations, much as we've seen before. And now the components documentation. But now we need to understand if there is a couple of different files or tables that document these processes. It's completely fine. But what we need is a key to combine data points from different stations. So this is an example, and for every data point or for every system, we need to link different components and different parts in it. Relying on timestamp might seem like a good idea, but it's usually not a good way to combine data sets because it's mostly not reliable because every timestamp looks different and sometimes traceability is lost throughout the machines. Now let's touch on the amounts of data. So the more variables we have, of course, related to much more complex manufacturing process means we need more data. So the exact amount varies from case to case and depends on the coverage level. So on what parameters are we actually able to trace and the yield of the process because that defines how many bad examples we have to learn from. However, a good rule of thumb is 10x examples, 2 parameters. So for example, if we have a 3-step process with 10 parameters at each step, we would require a minimum data sets of 300 serial numbers. Another key aspect of training machine learning and deploying machine learning in manufacturing is not only to find a very good performing model, but it's also to provide explainability. Explainability is important because engineers need to understand what is the driving factors or what is impacting the predictions. It is very important for trust, and also if we need to iterate those machine learning model building, then we need to understand what is driving the prediction. This is what we put a lot of focus in Vanti. So, for example, if we're talking about images, it's to be able to say which product codes and which product types are driving each cluster. What if we need to fine tune it or exclude some data points. And also in our daily reports, what we're doing is basically pulling out those insights from the data for increased likelihood of failures or a combination of tests. So manufacturing experts can really take an active approach and understand what's driving the AI process. So now let's go to deployment. You have a good model, you pre-trained it based on historical data. Now, how does it look like in production? So let's look at a specific example. This is again an assembly test process for electro-optical module. And here, what we see is that data is collected from 3 different testing points. It is saved in this example on an historian or database of the customer, and then communicates through a 2-way API with the production model. The production model returns results in real time for every new single unit, whether it's going to fail or whether it's going to pass. In this way, of course, when you offload bad units from the line, you immediately increase the yield and the throughput of the line, and also you'll get those insights so you can do the rework or investigation or the continuous improvement of the line. Of course, we need to also always guarantee the availability and monitoring of the machine learning model, and you can either build that application by yourself or you can turn to a full stack solution like we do at Vanti.
So now after we discussed the entire workflow, I want to show you how would that look like on Vanti's application. So I will just quickly sign in with my account. I already have one. And what we see here are a couple of, okay, that's available as a desktop app as well. And what we see here are a couple of examples of pre-trained reports and projects, but let's quickly start a new project so you'll get a sense of how would that look like. So I'll just name my project. And now we get to choose what kind of model we actually want to build. So the first one would be early fault detection. That would be a classification model. So if we want to predict in early stages what will happen at later, what will fail eventually at a final station. So that is a classification labeled model, meaning that we already have historical data of failed and passed units at the end of the line or any other station we want to predict. The second part is really finding faulty units at a specific station. Usually that is very applicable for stations that are taking images, so X-ray, AOI, some kind of any type of metrology tests. So to be able to train a model, either unsupervised or supervised, meaning that we have labeled data or not. So we will just divide it to clusters and try to figure out what are defects and what are not. And the final part is process optimization, where we want to build a regression model. We want to understand a number, or we want to predict a number or a set of numbers, a vector, to fine tune our process, to be able to do it as fast as possible and get the best results from that station. So we'll have a look at the sample report from that. But for now, let's just build a new model for early fall detection. So what you will upload here, what you'll connect, is a tabular data set. So it can be an Excel spreadsheet, it can be a CSV file, a bunch of them, like we discussed before, with traceability. But for the time being, let's just use just one CSV file as an example. So I just uploaded that file, and now we have a snippet of the data. So what we see here are a bunch of different serial numbers and a lot and very, very big number of tests. So you can see it can be continuous values or just 0, 1, like binary results. There can be missing values, whatever is inside, we can handle it. And let's just jump very quickly to the end, and we'll have that KPI column. So the KPI column is what we want to predict. In this case, whether the unit failed or passed that station. That would be the goal for prediction. So now we get to the configuration and settings of the model. So either you just go with automatically, so we'll find and recommend the best working point for you, or you can go with manual, where you can define your sensitivity to escapes for maybe units that we will not be able to pick up on the expense of being very precise. So that is the trade-off between the cost of failure and the cost of mislabeling. So maybe saying for a good unit, it's actually a failed unit, and then you will lose maybe a bit of time. But that really depends on your threshold. Maybe the cost of failure is so high because failure on the side of the user or your client is very high, or you cannot rework it. So then, and you have to scrap the entire thing. So you can choose and fine tune it. You can tweak it, just scroll around here, and you can iterate on it as you go. So in addition, you can also refine the data, the different parameters. You can exclude you can exclude it altogether if it's not relevant, or maybe it shouldn't be in the data set, or maybe it's duplication of another parameter, or it's really dependent on it, or you cannot even change it. So you have no control of it, or maybe just defining different values to it. So maybe everything that is more than 100 is irrelevant. So you can do that again for every parameter. And what we see here is for even more advanced users to customize features. If you know in advance what would be features that have impact, or you want to pre-process the data with some built-in algorithms or models. So you can do that as well. So now the data is uploading to for training. As you can see, it happens really quickly. And now you'll get a message that basically everything's okay, good to go. That will take usually a couple of hours. So you can see now it's analyzing. We won't wait for a couple of hours. We'll just jump quickly to what's happening once we finish to train a model. So the thing that will happen is that you will get a report about the performance of the model. So what were we actually able to train? You will get the accuracy of the model, and then really a breakdown of what does it mean when Vanti says fail, And what does it mean when Vanti says okay? So out of 100 failed units, we will pick up and predict 90. And out of 100 units that we will label as fail, we will be wrong in six units. So that is the trade-off I mentioned before. It's never 100%, and you can fine-tune and tweak it as you like according to your internal costs and goals. Also, we'll provide those insights where what we mentioned before about what increases the likelihood of failures. In this case, it was a combination of two tests and different thresholds. And now you can go ahead, train another model, or just deploy it. We'll see that in a second. So let's look at image classification example. That is a report we will produce. In this case, it was unsupervised, so we just divided. So we didn't know, we didn't have labels of what's actually failing and what's a good unit. So we just found a couple of groups that have similar attributes, that have similar behaviors, and everything we can tell you about that, so you can take a very informed decision whether it represents and describe your line in your units in a good way. So we will give you a sample of the different clusters, so sample of images from every cluster. And if it's in the data, we'll also tell you what are the product codes that are responsible for this cluster. We'll also tell you the fail rate, so you can double check and see if it makes sense with your yield at that station. So if you're at 97, 98% yield, so definitely you'll be able to say, okay, the things we are labeling as failed units or defected units, we know that are actually correct. And there are a couple of more things that we can tell you, but we don't have a lot of time for this demo. So the last thing I want to show you is a regression model. Regression model basically means how good are we able to predict a single or a vector of numbers. In this case, it was a calibration station, which replaced a fine-tuning a vector of numbers quite in a trial and error kind of way to an automated way, which really reduced the calibration time all the way from 40 minutes to just a couple of seconds, the round trip. And 0.92 is the R2 score. So it's a very, very good accuracy. And also some insights about the data. Again, what are the key driver factors? Maybe some redundant measurements where you can have maybe another additional value in reducing the cycle time for testing, and also maybe some data about the data to add more samples to increase the accuracy of the model. So what I didn't touch is now if we want to deploy the model, you will get all the documentation. Basically, you get an endpoint in the cloud where you can set up the two-way API and get predictions in real time. All the documentation is here. It's very simple. And lastly, in production, once the model is deployed, it's continuously monitored, and you will get a status report every time things are changing, or just on a daily basis in our web app or directly to your mail. With the numbers for, in this case, early fault prediction. So how many units we actually labeled as failed, and all of those insights about the different combinations of tests or materials or parameters of the process that increases the likelihood of failures, and maybe things that have changed in the recent couple of hours or days, and some improvement possibilities if needed, or a retrain request if needed.
So that may sound a bit intimidating, but it's really worth the effort. And what we've seen from many use cases is that the benefits of deploying machine learning models in manufacturing can dramatically reduce cycle times of manual or trial and error process tuning. We've seen examples all the way down from 40 minutes to for 4 seconds, so automated completely. Increasing the defect detection coverage, so very fast deployment, training of capabilities to detect real defects in images. In the previous example, we've seen an improvement in throughput and also reduction in material and failed units. So again, machine time, and also all the way to detection of RMA units. So predicting in advance what will fail in the field. Sorry. So that is all I wanted to share today. Very happy to hear your thoughts and questions, and feel free to reach out if you want to learn more. You can find us at info@vantianalytics.com.